This is kind of a quick introduction to nonlinearities and other functional forms. It's sort of a teaser for what we'll talk about later on in the semester. Okay, so far all we've considered is a linear relationship between y and x. The regression line of, let's choose a different color. How about blue? We haven't used blue. The regression line of yi plus equals beta 0 plus beta 1 xi plus u. That's a linear relationship between y and x that only allows for a straight line. Suppose we wanted to know the effect of education on wages. So we're back to this wage and education example. We regress wages on education and get the following relationship. Wage hat, the predicted wage, is equal to 10 plus, ooh, I made a mistake here. Somebody watching this should pick up on this. Wage hat equals 10 plus 0.54 times education plus u. What is my error in this equation? Well, we know that we can write the sample regression in two ways. We can write it as the predicted y variable times the x, or as a function of the x variable, or we can write it as the data points without the hat, wage without the hat, as a function of the regression equation plus the residuals. I've added both into this equation, and I actually added the population residuals. So this is wrong on two fronts. I added the population error term, or the population residuals, to a sample regression equation with the predicted wage on the left-hand side. So I either need the correct way to write this. The correct way to write this is either this way, 1, or 2 down here. So to make this correct, I should probably get rid of the u. Get rid of that. It has an r squared of 0.05. This says an additional year of education is predicted to increase wages by 54 cents per year, or per hour. This is true for 1 year of education and 22 years of education. So if you start at 1 year of education, 1 more year of education is going to get you 54 cents more per hour. If you start at 22 years of education, 1 more year of education is going to get you 54 cents per hour. So this kind of highlights the idea that we're dealing with a linear function, like we wrote up here, a linear relationship, and some of the problems with it. It assumes that the average effect of education is the same across the entire spectrum of the x variable, in this case education. The r-squared says that only 5% of the variation in wages is explained by education. Can we do better? Maybe a better way to think about this is that each year of education increases wages by some constant percentage rather than a constant amount. A constant percentage increase in it is captured by the following model, where we go log wage is a function of education. This results in, if we ran this regression, we would have, okay, let me take one step back because this is always confusing. What do I mean by log wage? In our data set, we're going to have wage as the dependent variable. If we were looking at our spreadsheet, we would have rows, right? I've said this before, indexed by I. Maybe wage in the first would be like $15 per hour, and the second would be $14 per hour. When I say log wage, all I'm saying is we create another column in our data set called log wage, where we take the log of the wage. So whatever log of 15 is, that would go there. Log of 14 would go here. So basically we're just creating a new column in our data set and using that as the dependent variable, or the y variable. If we did this, it would result in the following equation. Log wage hat is equal to 0.584 plus 0.83 times education, with an r-squared of 0.186. So the interpretation of this equation is that 1 year of education increases wages by about 8.3%. So that's how we're interpreting this beta 1 hat coefficient, the slope coefficient. This is a constant percentage, meaning that, like on the previous slide, we said at 1 year of education and 22 years of education, an additional year of education would increase wages by 54 cents per hour. Now we're saying at 1 year of education and 22 years of education, another year of education is going to increase wages by 8.3%. And so that's going to mean that at 22 years of education, wages are going to increase more in absolute value than they would if you had 1 year of education. Presumably, wages start at a higher value with 22 years of education. If r squared is higher when the dependent variable is in logs, this means a better fit of the data, and that's indeed what we find. In the previous example, with a level regression, the r squared was 5%. Now we're up to 18%, or 18.6%. So that says that we're doing a better job predicting the y variable when we have log y. So it's a better fit of the data. Okay, some common functional forms. We have level. This is what we've been talking about all throughout this set of lecture notes. This is when we're regressing y on x, the level of y on the level of x. And the interpretation of beta, the slope coefficient, is a change in x. 1 unit change in x causes a beta 1 unit change in y. A beta 1 change in y. Then we can have level log, where the y variable is in levels and the x variable is in logs. And the interpretation of the beta in this regression would be a 1% change in x causes a beta 1 divided by 100 change in y. So the idea here is that when we log a variable, either the x or the y variable, now we're talking about percent changes in those variables. We could have log level, that's the third line here. So now we're logging the y variable. This is what we did in the previous example. We're logging the y variable, but leaving the x variable as is. And so the interpretation of the beta 1 coefficient in this regression would be a 1 unit change in x causes a beta 1 times 100% change in y. And then this is called a semi-elasticity. And then we have log, final one. This is a log y and log x. So this is a 1% change in x causes a beta 1% change in y. This is nice because this is actually an elasticity, and we can use it to estimate demand elasticities or supply elasticities. So for example, if we were trying to figure out the elasticity of demand elasticity for gasoline, we could regress the log of gasoline consumption on the log of the price of gasoline, and maybe we got negative 0.2, meaning the demand elasticity, QP, right? Demand elasticity, how steep is this line, is negative 0.2. So we're directly estimating something that we talk about in microeconomics. We talk about demand elasticities all the time. Now we're finally connecting econometrics to what you might have studied in a previous course, demand elasticities.